Today I want to talk about how you can find the mean of a general random variable. Not just a discrete like we've talked about before, but about a continuous or a function of a random variable. As always, let's start with a story. The wizard threw yet another fireball at the approaching monsters, then glanced backwards. Where were the reinforcements so desperately needed? The wizard had modeled the time until the reinforcements came as exponentially distributed with rate parameter 0.3 per minute. With that model, what was the expected number of minutes until they arrived? Now, last time an important fact was stated. The mean of an indicator function is just the probability that the event inside the indicator function is true. So for a random variable x and measurable set a, the probability that x is in a is the mean of the indicator that x is in a. Of course, there is another way to find probabilities. Use the density of x. The probability that x is in a is the integral over a of the density of x at little x with respect to the measure, which is the integral of the indicator that x is in a times the density of x at little x with respect to the measure. So that means that the mean of the indicator that big X is in a is the integral of the indicator that little x is in a times the density of x. Using linearity of expectations, this can be extended to weighted sums of indicator functions. So to find the mean of 3 times the indicator that x is in a plus 2 times the indicator that x is in b, use the integral of the quantity 3 times the indicator little x is in a plus 2 times the indicator little x is in b times the density of big X at little x with respect to mu. In general, if h of x is any weighted sum of indicator functions, then the mean of h of capital X is the integral of h of little x times the density of big X at little x with respect to the measure mu. That tells us how to find the expected value of a function of a random variable with a density when the function is the weighted sum of indicator functions. Now, even if the target function is not exactly a weighted sum of indicator functions, a weighted sum of indicator functions might be good enough to approximate the function. For instance, consider the following 4-interval partition of 0 to 1. We have I0 is 0 up to 1/4, I1 is 1/4 up to 1/2, I2 is 1/2 up to 3/4, and I3 is 3/4 up to 1. Then if I take 0/4 squared times the indicator x is in I0, plus 1/4 squared times the indicator x is in I1, plus 2/4 squared times the indicator x is in I2, plus 3/4 squared times the indicator x is in I3, then that is an approximation to the function y equals x squared over the interval from 0 up to 1. Pictorially, the approximation looks as follows. In the blue, you can see y equals x squared. In the green, you can see this weighted sum of indicator functions. Now, the idea is by using more and more indicator functions, the approximation gets better and better. This leads to the following way to calculate expected value for random variables with densities. The expected value of g of x equals the integral of g of little x times the density of big X at little x with respect to the measure mu. In general, this result is one of the most important in probability theory. Suppose that random variable x has density f sub x with respect to measure mu. Then for a real valued function g, the mean of g of capital X is the integral of little g of x times the density of x at little x times the measure mu at x, if that integral exists. Now recall that our two most common measures are counting measure for discrete random variables and Lebesgue measure for continuous random variables. For Lebesgue measure, the integral from g of x of f of x with respect to mu is just going to be the integral with a dx at the end. For counting measure, the integral of gx f sub x of x with respect to a differential of counting measure will turn into the sum over x of g of x times the density of big X at little x. This is summarized in the following result. If x is a continuous random variable with density f sub big X of little x with respect to Lebesgue measure, then to find the expected value of g of capital X, you do the Riemann integral of g of x times the density dx. For x a discrete random variable with density f sub big X at I equal to the probability that x equals I with respect to counting measure, the mean of g of x is the sum of g of I times the density of big X at I. This result is sometimes called the law of the unconscious statistician, since every instance of the random variable big X is replaced by the index variables in the integral or sum. We can see that in the integral, g of big X gets replaced by g of little x, and in the discrete random variable, g of big X gets replaced by g of little I. So for example, suppose that I want to set up the integral for the mean of the exponential function applied to t, where t is a uniform random variable from 0 to 10. Now t is a continuous random variable with density f sub big T of little t equal to 1/10 times the indicator that little t is in the interval from 0 to 10. Hence the mean of e to the big T is the integral of e to the little t times 1/10 times the indicator that t is in the interval from 0 to 10 dt. Now we can take that indicator function and use it to say we're integrating from 0 up to 10 e to the t divided by 10 with respect to dt. Now for a discrete example. Suppose I want to set up the integral for the mean of w squared, where w is uniform over the set 1 through 5. Now because w is a discrete random variable, the quote-unquote integral becomes a sum. And we're just going to sum as I goes from 1 to 5 I squared, because we're finding the expectation of w squared. And we're going to multiply it times the density, which is 1/5 for each of those numbers for I going from 1 up to 5. Suppose I wanted the integral of the square root of t, the mean of that value, where t is an exponential of rate 1. Well, the density for that is the exponential function applied to negative t times the indicator that t is greater than 0. So the indicator is the mean of square root of t is the integral of square root of t times e to the negative t times the indicator that t is greater than or equal to 0 with respect to dt. We can use the indicator to change the limits to 0 to infinity of square root of t times e to the negative t. In the case of the story, the goal was to find the mean of t, where t was exponential with parameter 0.3 per minute. The density of big T at little t is 0.3 times e to the negative 0.3 t times the indicator that t is greater than or equal to 0. And here our function g of t is just t itself. So the expected value is going to be the integral of t. Note the big T out in the expectation becomes a little t in the integral times the density of the exponential. We can use the indicator part of the density of the exponential to change the limits to 0 to infinity. Then we have to use integration by parts. So I'm going to write this second part as the derivative of negative the exponential of negative 0.3t. Then apply the integration by parts formula to say that that's negative t times e to the negative 3t evaluated between 0 and infinity, minus the integral from 0 to infinity. Moving the derivative over to the t part, we get negative derivative of t times exponential of negative 0.3t. This first part is just going to be 0 because when t equals 0, I get 0. And as t goes to infinity, the e to the minus 0.3t dominates the t. So all we're left with is this final integral, which we can anti-differentiate e to the minus 3t to bring down a negative 1 over 0.3 times e to the negative 0.3t, again evaluated between 0 and infinity. The infinity part is going to 0. All we're left with is the 0 evaluation, which gives us 1 over 0.3, which is about 3.333 minutes. So in other words, if I have a random variable that is exponential with rate parameter lambda, the expectation is going to turn out to be 1 over lambda, which is kind of nice. Very simple. Now, earlier it was noted that for integrable random variables that are symmetric about m, the mean must also be m as well. And this works equally well for continuous as well as discrete random variables. Suppose that x has density f sub big X of little x with respect to Lebesgue measure, where f sub x at x minus m equals the density of x at m minus x for some constant m. Then if x is integrable, then the mean of x equals little m. Now both discrete uniform random variables over the integers from a up to b and continuous uniform random variables over all real numbers from a up to b are symmetric around the center of this interval, which is the quantity a plus b over 2. Moreover, each has a finite expected value because they are bounded below by a and above by b. Together, this gives the following result. If I have a random variable x, which is uniform over a set A, and A is the integers from A up to B, or A is the real numbers from A up to B, then the mean of x is just the average of the endpoints, A plus B in the numerator over 2 in the denominator. Now the term Monte Carlo method refers to any algorithm that draws from random variables while running. One type of Monte Carlo method can use random draws to estimate sums or integrals. For instance, suppose that the goal is to estimate the integral I, which is the integral from 0 to infinity of t to the 3/2 power times the exponential function applied to negative t. Well, note that capital I is the mean of capital T to the 3/2, where t is an exponential random variable with mean 1. So we can use the strong law of large numbers. We're going to draw n IID copies of capital T, where n is a large number, then take the sample average of the results. In R, this can be accomplished with code that does the following. N gets assigned the value 10 to the 6th, a million. T gets assigned a draw of that million exponential random variables of rate 1, and then we're going to print the mean of t raised to the 3/2 power. The result when you do this is going to give you an answer very close to the true answer of 1.32934. So that's how you find the mean of a general random variable. You take the integral of the function of the random variable times its density with respect to its measure. See you next time.